What prevents a time machine from becoming real? To answer this question, I look through various popular science sources and draw on science fiction. We proceed only from the fact that physics itself forbids such devices. The next group of approaches is a description of the technologies. We assume that the technologies that exist today or will exist in the relatively near future are in no way capable of accomplishing anything that Doc Brown did in his garage. And unfortunately, creating a flux capacitor without resorting to science fiction is still impossible for now, but all these points, both theoretical and practical, are only indirect. And one of the main principles, which for some reason always remains out of focus, is actually more related to chaos theory, right, my friends? And today we are going to figure out why, in fact, building a time machine is impossible, or at least impossible for now. Let's start with the most important thing. I said that physics seems to limit the possibility of a time machine, but if you delve into the study of various theories, if you use the existing classical approach, you'll find out that physics, in general, does not actually limit the time machine. Physics does not forbid the time machine, and the laws of physics work both ways. They are, well, if you set aside the quantum world, symmetric in time. And this means only one thing, that physics treats time as a certain entity that is measured by clocks. And this means that with this approach, we can freely travel along the arrow of time both forward and backward. But the real problem actually lies elsewhere. When we imagine time travel, we picture it in our minds as a certain point. And it's not just us, not only those who are interested in time machines and various theories, but scientists do the same. This doesn't mean that we resort to such simplified approaches out of some incompetence. It's just that the concept perceives this way of solving the problem in exactly this manner. We have space and we have time. We remember that space and time are interconnected through the speed of light, according to Einstein's work, and we remember that this is an inseparable thing. This means that every point in space has spatial and temporal coordinates. But for simplicity, for now, we'll focus only on the arrow of time. Basically, in order for us to move from here to 50 years ago, or 50 years into the future, we just need to slide the pointer along the time scale forward or backward. The laws of physics can't stop us here. We do remember that the laws of physics are supposed to be symmetric in time. And by the way, that's one of the fundamental principles of physics. Just for the record, this means that physics not only doesn't forbid time travel, it actually allows it. And we should definitely consider at least classical mechanics. And most of the laws we learn about in school or university as laws that work like a reverse meat grinder. It is with this kind of basic physics that we measure a time machine. We imagine that the very slider you move along the arrow of time will, with the highest precision, describe the state of the system we have. Now let's return to the complexities that, in fact, we need to take into account here. Let's go back to that very volumetric system you were imagining. All right, suppose in this system a cyclist has just left point A for point B. In order to bring the cyclist back in this system, you simply need to move them within the system to the point that interests us. And it would seem that at this point, the time machine should stop. This is exactly what needs to be achieved technologically. This is precisely what should allow us to travel through time and put us on par with the legendary Doc Brown and other scientists capable of moving through space-time continuums and splitting the fabric of space-time. But no, it's much more complicated than that. We drew ourselves a single coordinate cube, but it doesn't just exist in a cube, it exists in the universe. You can't even imagine it. And I'm not joking. There have been studies that have shown that humans are not capable, technologically speaking. Neither you nor I nor anyone else is capable of comprehending the size and scale of the universe. We simply don't have the capacity for it. It's like we're trying to run a Dreamcast game on a Dendy console. And unsurprisingly, it doesn't work. That's pretty much the same story here. We can't process the information that the universe is infinite on our mental hardware. So let's imagine yet another simplification. Let's imagine that the little cube in which the cyclist was traveling, the one we want to move from point A to point B, suddenly finds itself inside another, much larger cube. And in this huge cube, there are other objects as well. And while we were talking about the cyclist moving from point A to point B, there was also a comet flying alongside him from point A to point B. Theoretically, this comet could accidentally flatten the cyclist if it hits him. It could also influence various gravitational factors, and many other things could happen as well. This means that no system exists in isolation. And now it's time to recall the concept of closed reference systems, or more precisely, just systems, closed systems. The word reference isn't there. A closed system is a kind of simplification. And if you studied physics carefully at school or university, you probably had the question, how is that possible? A closed system that's isolated, that doesn't interact with other systems. What kind of nonsense is that? And yes, my friend, you're absolutely right to think that way. You're awesome, and that's exactly why you're watching my channel. Give it a like, it turns out the textbook should have been written a little differently. It should have said that a closed system isn't a system that somehow miraculously exists, isolated from other systems, but rather a system where we're simply not interested in the influence of other systems. And what do we do next? Next, we analyze the system that we have, this overall system. We said that the cyclist who is riding in a cube from point A to point B is now no longer moving separately from everything else. He is moving within the whole system. And here we need to remember something else. Perhaps you've heard, at least in passing, about the so-called three-body problem. Even classical mechanics, even the father of mechanics, Newton, tried to analyze this, but of course he didn't succeed. What is the idea behind it? It's pretty much the same as what we discussed with the cyclist, only applied to planets. Let's take two balls that are in this room. As long as these two balls are in this room and are somehow isolated from the rest of the world, we can calculate precisely, based on the reversibility of the laws of physics and the ability to make predictions using mathematical tools, that the ball rolling relative to the other ball will, in 5 minutes, end up at point B with such and such coordinates. As long as everything is isolated, everything is great, everything can be calculated. Alright, we can add a third object to this isolated system. Let's add a third ball. When we add some third object to this system, for example, a planet, some body near this planet, and a third planet, and now try to calculate how all of this will evolve over time, how things will move, for instance, how a comet will move relative to these two bodies at once. This is where we run into trouble. This is where the scariest thing imaginable begins. This is where it becomes impossible to calculate. Why? Well, I hope that from the examples with the cyclists you already understand this, and maybe you've heard of the three-body problem before. The problem is based on the fact that we can't predict the factors that will influence it. And maybe now you understand where I'm going with this. I'm leading up to chaos theory. In fact, that's where we started. Chaos is a very frightening thing. Chaos isn't scary because it's absolute disorder. That's a common misconception. Chaos is frightening because it's actually order. But this order is so complex that it's impossible to calculate. If you're interested in hearing more about chaos specifically, let me know in the comments. I'll try to prepare a video about chaos, because we'll encounter chaos many more times in our physics course, in our study of various interesting processes. And so, when we talk about chaos, it's helpful to imagine an interesting example. Let's use the weather as our reference point. There is well-established information, solid scientific knowledge, that it's impossible to predict the weather for more than, I think, 2 weeks or a month or something like that. Please correct me in the comments if I'm wrong. This is not a joke, and it's not a criticism. Those who forecast the weather, the system itself is simply limited by these kinds of parameters. How should a time machine work? It should be a technology that connects point A in space to point B. What's needed is for the space of the time coordinate here and the space of the time coordinate there to become movable. I probably said that awkwardly. Everyone's going to get confused. Let me put it more simply. In order to move to the arena, I need to take an object and transfer it from this point to that point. This point has coordinates, and that point has coordinates too. As long as this is a local system, we really only encounter the fact that there is no technology capable of affecting our ability to create wormholes in space, or to move in some other way to make bubbles like our legendary and beloved Doc Brown did, or to build other devices that can split the fabric of space-time and so on and so forth. But this only matters when we are working within a certain isolated system, and we have already given at least 3 serious examples that isolated systems do not exist in science. And we must proceed from the fact that we move through time based on patterns related to chaos. Just as we cannot accurately or objectively forecast the weather for more than, say, 2 weeks ahead, we also cannot predict the state of a system for more than, let's say, it's hard to say what the actual numbers would be, but essentially we cannot describe this system mathematically. Now, based on the knowledge we have, we can confidently say that we cannot move to this coordinate because the coordinate no longer exists or it is in a different place. A simple example, right now I am here and let's say I want to move 50 years into the past. What would happen if I moved here 50 years back? Well, there might be something like maybe a forest, maybe a field, or maybe even a mountain. Anything could be there. This is the uncertainty factor. And that's if I'm lucky enough to end up in a field or even on the same planet. But we have to remember that the whole system is moving. We have to remember that nothing in space is truly stable. We have to remember that planets are constantly shifting and that there are factors influencing all of this. And most likely, if you try to move directly by the coordinates we have, assuming that the arrow of time should take you from point A to point B, then point B will very likely end up somewhere on the moon or in the center of the sun, which you'll agree isn't very good for the traveler. You might say that modern computers can't do that, but in another 50 years or so, computers will be able to calculate the parameters we're interested in. And that the whole problem I mentioned comes down not to fundamental limitations of physics or anything like that, but specifically to technology. But here I would counter that yes, you're right, as long as the system is relatively simple. But we will be dealing with a chaotic system. We will encounter the fact that we cannot predict the state of the system. For some reason, this problem isn't really considered when discussing time travel.